Hello guys, welcome back to my channel, and in this video I would like to take some time to actually prove some identities of the Dilogarithm function that we've so extensively used in some of the previous uh, videos in the trig integrals playlist. Okay, so as always, let's get started. Okay, just to give you a brief introduction about polylogarithms. So, polylogarithms are basically denoted by Li subscript s of z. So, polylogarithm of order s having an argument of z is defined as sum from k equals 1 to infinity of z to the k power divided by k to the s. So you can say see that they're sort of a generalization of the Riemann zeta function. They just have this argument part of z in the numerator. Otherwise, they're pretty much similar to uh, the Riemann zeta function. Now, dilogarithms are a special case of polylogarithms. They're basically polylogarithms of order 2. So they're denoted by Li sub 2 of z is actually equal to sum from k equals 1 to infinity of z to the k over k squared. And in this video, we're primarily going to deal with this dilogarithms. Now, apart from simply having this infinite sum definition, there's also integral definitions for the dilogarithm. So the dilogarithm of z is or can be given by negative integral from 0 to z of natural log of 1 minus t over t dt. And proving this is pretty easy. What you do is you use the Taylor series of this natural log. So you have sum from k equals 1 to infinity of minus t to the k. Don't forget the minus 1 to the k plus 1, the alternating part, divided by k t dt. So we have negative sum from k equals 1 to infinity minus 1 to the k plus 1, negative 1 to the k all over k, integral from 0 to z, t to the k minus 1 dt. So the minus 1 to the k is becoming an even power, will just be 1, and we have minus 1 to the 1. That negative will cancel out with this. So we finally have sum from k equals 1 to infinity of 1 over k. This, after performing the anti-differentiation process, will be k squared, and we'll have t to the k evaluated from 0 to z. So when you plug stuff in, you just have sum from k equals 1 to infinity of z to the k over k squared, which is indeed your dilogarithm according to our original infinite sum definition. Now there is another formula, but for the dilogarithm of 1 minus z, that is given by integral from 1 to z of natural log of t over 1 minus t dt. Now, like the one before this, we can simply use the Taylor series. So I'm just skipping, I think, one step. We have sum from k equals 1 to infinity of minus 1 to the k plus 1 over k, and then we have t minus 1 to the k over 1 minus t, integral from 1 to z dt. Now what I'm going to do is I'm going to actually factorize out minus 1 to the k from this term, which was, raised to the kth power collectively. That will make me enable uh, switching of the order of this, whatever was inside. So we'll have minus 1 to the k that we basically factorized out, integral from 1 to z, switching the order because we took out a negative from, well, k terms, 1 minus t to the k over 1 minus t dt. So the minus 1 to the k's will be becoming an even power, will cancel out to 1. We have negative sum from k equals 1 to infinity of 1 over k, and then this is integral from 1 to z of 1 minus t to the k minus 1 dt. Now performing the anti-differentiation process, you have sum from k equals 1 to infinity of 1 over k squared 1 minus t to the k evaluated from 1 to z. So this will just become sum from k equals 1 to infinity of 1 minus z entire thing to the k over k squared, which by the definition just happens to be a Dilogarithm of 1 minus z. Again, using the original infinite series definition. So these are basically some of the formulas that we're going to be using for some of the identities that I'm going to prove coming up. So, okay, let's get started with proving identity. See you on a fresh page. Okay, so the first identity we have is the reflection formula, and almost like the digamma function, if we add dilogarithm of z plus dilogarithm of 1 minus z, you get something exciting. So I'm just going to use the integral definitions of both of them that I actually discussed in the introduction part. So we have negative integral from 0 to z of natural log of 1 minus t over t dt plus integral from 1 to z of uh, well, natural log so you have natural log of t divided by 1 minus t dt. So now what I'm going to do is I'm going to actually perform integration by parts on this. So naturally we'll be integrating this 1 over 1 minus t, and sorry, I wanted to put an I there, and we'll be differentiating this. So write the first as it is, natural log of 1 minus t over t dt. This can be expressed as, well, take a negative to compensate for the negative of the antiderivative. Natural log of 1 minus t times natural log of t evaluated from 1 to z minus minus plus integral from 1 to z of natural log of 1 minus t over derivative of natural log of t is just t dt. Okay, so we have negative integral from 0 to z of natural log of 1 minus t over t dt plus integral from 1 to z of natural log of 1 minus t over t dt. And over here, when you just plug stuff in, you have natural log of 1 minus z times natural log of z, and when you plug in 1, you'll have natural log of 1, and natural log of 0 basically. So it's basically a 0 times infinity situation, which will roughly just go down to 0, right? Because you can do L'Hopital rule, you can do whatever you want, but anyways, it's just going down to 0 eventually. If you don't believe me, you can do it on a piece of paper using some identities if you want of limits. But basically, the at evaluated at 1, this is going to 0. Okay, so we have integral from 0 to z with a negative, and added with integral from 1 to z of basically the same integrand. So we can apply linearity of integrals. So notice that we have basically integral from 0 to z. So this is 0, this is z, which is actually a negative. And then to that, you add integral from 1 to z. Here's 1 and here's z. So, having opposite signs is basically subtracting this off. So, we're remaining with negative integral from 0 to 1, right? Because that's all that remains on this interval after subtracting and stuff. Natural log of 1 minus t over t dt minus natural log of 1 minus z natural log of z. And now we can actually use some Taylor series. So sum from k equals 1 to infinity of 1 over k integral from 0 to 1 t to the k minus 1 dt minus natural log of 1 minus z natural log of z. So this becomes integral from sum from k equals 1 to infinity 1 over k squared t to the k evaluated from 0 to 1, which will just become 1, minus natural log of 1 minus z times natural log of z. And this is just the Bessel problem, right? Riemann zeta of 2, which is pi squared over 6, minus natural log of 1 minus z times natural log of z. And all this is actually equal to Dilogarithm of z plus Dilogarithm of 1 minus z. That's the reflection formula for the Dilogarithm function. Okay, so now what happens when we have Dilogarithm of 1 minus 1 over z plus Dilogarithm of 1 minus z? Well, let's use the integral definitions of these things. Okay, so for this integral definitions, as I said, so we have integral from 1 to 1 over z, because of this 1 over z over here, of natural log of t over 1 minus t dt plus integral from 1 to z of natural log of t over 1 minus t dt. So the only ugly looking expression is this with the reciprocal upper bound. So what we're gonna do is actually have a clever substitution. So let t equal 1 over y. So dt is equal to negative 1 over y squared dy, enabling us to write this as integral from 1 to z. That's why we convert the reciprocal to a regular upper bound using this substitution. That's why this is useful. Natural log of 1 over y divided by 1 minus 1 over y, and we have 1 over y squared dy. Well, the negative went in correcting this. Well, no, we still have the negative, my bad. Yeah, and we still have this other thing over here, 1 minus t dt. Looks like we can still do some simplification. So we have integral from 1 to z of natural log of y over y times y minus 1 dy plus integral from 1 to z of natural log of t over 1 minus t dt. And now just using partial fraction decompositions 1 over, for which I don't even need to do the complete calculation. We've integral from 1 to z of natural log of y over y minus 1 dy minus integral from 1 to z of natural log of y over y dy, and we have, well, I'm gonna just take a negative out from the second integral, natural log of t over, when I take a negative I'll have to switch the order of this denominator like this, and lo and behold these two are actually the same. It's just changed up variables, but since these are definite integrals, it doesn't matter what variable we have, as long as the form and the upper and lower bounds are the same, so they cancel out nicely because of the negative. So all we're left with is negative integral from 1 to z natural log of y over y dy. You can use your u substitution, noticing that the derivative of natural log is present, so you'll just get negative natural log squared of z over 2 y rather, evaluated from 1 to z. So now when you plug stuff in, you have natural log squared of z over 2 plus natural log squared of 1 over 2. Natural log squared of 1 is going to be 0. So all we are left with is negative natural log squared of z over 2, and that is precisely equal to the dilogarithm of 1 minus 1 over z plus the dilogarithm of 1 minus z. Isn't that neat? Okay, so moving on to the last identity of the day. So now what we're going to do is we're going to have the dilogarithm of z being added with the dilogarithm of negative z. Okay, and so for that again I'm going to just use the integral definitions of, well, both things. So if negative integral from 0 to z of natural log of 1 minus t over t dt minus integral from 0 to negative z natural log of 1 minus t over t dt. And like formula number 2 that we had, we're going to look at this ugly expression and do some substitutions to probably change it. So let t equal negative y. So we have dt being equal to negative dy. So write the first integral as it is. Making this substitution, we have negative integral from 0 to z of natural log of 1 plus y over negative y dy, and a negative which cancels out over here nicely. So we just have negative integral from 0 to z of natural log of 1 minus t over t dt minus integral from 0 to z of natural log of 1 plus y over y dy. And we can change from t to y, because again definite integral doesn't matter what variable we have, and we can basically club these two together. So natural log of 1 minus t plus natural log of 1 plus y, sorry, over y dy, like that. And now using some log properties, we can have product of these. So difference of squares identity again, natural log of 1 minus y squared over y dy. And now going for the quick substitution, let y squared equal to w will give us negative integral from 0 to z squared. This will mean dy is equal to well, 1 over square root of 2 1 over 2 times square root of w dw. So if natural log of 1 minus w over this half square root of w, and this y will also have a square root of w here like that. So we have minus half of integral from 0 to z squared of natural log of 1 minus w over w dw. And look at that, this is just the formula, the integral representation of the digamma of the dilogarithm of z. Well, the half is like an added factor, but we have dilogarithm of z squared now, because the dilogarithm argument was always the upper bound of this expression, so z squared. So we have dilogarithm of z squared over 2, which was the result of basically adding the dilogarithm of z and the dilogarithm of negative z. So yeah, pretty neat result again. So that's it for this video, guys. I hope you enjoyed this. I hope you learned a lot, and I hope this settles the agitating fact that I didn't prove this before, but now I'm doing it. So we're all fair, square, even Steven now. But before going, however, it would be my honor to ask you to like, share, and subscribe to my channel. Recommend me to your friends in the math community or anywhere. Just spread the word, guys. And in the meantime, stay home, stay safe, keep doing math, and peace out. And please stay tuned for more content from my channel. So, yeah, peace out.